In the previous section, we discussed this I claimed useful fact that if D divides A and D divides B, then D divides A plus or minus B. Here I'm writing A minus B. Okay, and we could have said that D divides like any multiple of A plus or minus any multiple of B too, right? But I'm very specifically leaving it like this here because I want to talk about why this is relevant to the following fact, and this fact is very useful for if you're trying to compute the greatest common divisors of two numbers. So let's say we're trying to compute the greatest common divisor of the numbers A and B. Turns out, because of this fact that I just mentioned, the greatest common divisor of A and B is going to be the same as the greatest common divisor of A minus B and B. So basically, instead of computing the GCD of these two numbers, you could take this number and make it smaller. So computing the GCD of smaller numbers is going to be much easier, right? So why is this true? Well, here's why. So let's say that D is equal to the GCD of A and B. Okay, so if D is equal to the GCD of A and B, that means D is a divisor of A and D is a divisor of B. So D divides A and D divides B. Okay, and therefore, because of this fact, D is also going to be a divisor of A minus B. So if D is the GCD of A and B, then D is going to be a divisor of A minus B and B. Okay, well, why does it have to be the biggest one? Well, you could do the same sort of trick. You could say that, well, if D prime is the GCD of A minus B and B, so D prime divides A minus B, and D prime divides B, then by that same fact, these two numbers, we could add them together, and then D prime would still be a divisor. So D prime would divide the sum of A minus B and B. What is A minus B plus B? That's just equal to A. So D prime is going to divide A. So if D prime is the GCD of A minus B and B, then D prime is going to be a divisor of both A and B. So any divisor of A and B is going to be a divisor of these two numbers, and any divisor of A minus B and B is also going to be a divisor of A and B. So A and B have the same common factors as A minus B and B, and so therefore the whatever the biggest one is going to be the same for both of them. So their GCDs have to be the same. Let's see how to apply this. Well, let's get rid of some of the mess here. So if I want to compute the GCD of 124 and 280, let's see how to apply this fact. So this says that if I want to compute the GCD of these two numbers, I could just take one and subtract it from the other to make it smaller. Right? So I guess the 280 is gonna take the role of A. This is sort of assuming that, like, oh hey, A is the bigger one, so we subtract the smaller one from the bigger one. It doesn't really matter which one comes first or whatever. So let's just subtract 124 from 280. What would we get? 280 minus 124, that would be 6. That would be 56. 156. And, well, you could see, like, oh, hey, we could just subtract 124 again. And what do we get? Well, we would get 32. So this would be the same as the GCD of 124. and 280 minus 124 twice, which is 32. Okay. Now you might notice that just subtracting repeatedly would get pretty tedious, especially if like this number is like many times bigger than this one. And so instead of just repeated subtraction, the repeated subtraction is really just division with remainders. And so we could have just divided 280 divided by 124 and then figured out what our remainder would have been. So we would have seen that this is equal to 2, and then our remainder would have been 32. And so we would just put our remainder here instead of having to do like this repeated subtraction thing. Okay, let's do that again. Let's do, so 124 and 32, these are still pretty big numbers. Let's make 124 smaller by repeatedly subtracting 32. I think that goes in 3 times, so 96. So that'll be, let's see, 428. Okay, so this will be 3 with a remainder of 28. So then this GCD is going to be equal to the GCD of, instead of 124 and 32, it'll be whatever that remainder is in 32. Okay, and these two numbers, these are much smaller and much easier to deal with. So you could keep doing this. You could subtract 28 from 32. You see, all right, that's going to be 28 and 4. And what's the GCD of 4 and 28? That's really easy to see because 4 divides 28. So 4 is a divisor of both 4 and of 28, so that has to be the biggest one because, I mean, it can't get bigger than 4. Okay, and so we didn't even have to do anything with like prime factors or figuring out what all the factors or divisors of any of these numbers were. We could just kind of repeatedly subtract stuff. Okay, you could have also at like any step along the way, if you could just kind of see like, oh, the divisors of or what are the factors of 28? Well, this is equal to 4 times 7, and this 32 is equal to 4 times 8. So 4 is going to be a common factor of both of these, but the 7 and the 8 here aren't going to have any common terms, so you could just sort of ignore those and then just say, oh, the GCD is going to have to be 4 because of that. Okay, so you could have stopped at any point along the way. Maybe you could even do that like at this step up here. I don't know. So part of the point of this is that you can sort of think flexibly. Another way that you could have done this problem would have been by using prime factorizations. Let me move this down. So I want to give myself some more room here. What if I wanted to do the prime factorizations of these two guys? So 124, how can we factor this? Well, let's see. Let's first factor out a 4, and that's going to leave me with 31. And so, let's see, I think 31 is prime. So I think this is just 2 squared times 31, whereas 280 is equal to, let's see, I could factor out a 4 from that as well. I'm left with 70. So that's 2 squared times, that'll be 2 times 35, and then 35 is 5 times 7. So this has a prime factorization of 2 cubed times 5 times 7. So 2 squared times 31 versus 2 cubed times 5 times 7. You can see like, oh, well, 2 squared is going to be a factor of both of these, or divisor of both of those. And so the rest of the other terms are not going to have anything in common. So the GCD would just have to be 2 squared. Okay. And if you, let's say that you found the prime factorizations of these two numbers. So GCD of, let's say 2 times 3 squared times 5 cubed, whatever that number comes out to. And let's say 2 squared times 3 times 5 to the 4th. what would the GCD of these two numbers be? Right. So turns out what you can do, since you know all the prime factors here, you can just kind of look at what the smallest exponent is for like each of these prime numbers, and then just use that. So here are the GCD. If I just go term by term, so 2, so I can't do 2 squared because 2 squared is not going to divide the first one, right? That would be too big. But just 2 by itself, or like 2 to the first, is going to divide both 2 and 2 squared, so I can do 2 there. Same reasoning for the 3. I can put a 3 here, but I can't put a 3 squared. That would be too much. And then what about for the 5 cubed and 5 to the 4th? Well, if I did, so it's going to be 5 cubed, because if I did 5 to the 4th, that would not divide 5 cubed. But if I did just 5 cubed, that is going to divide both 5 cubed and 5 to the 4th. So this is going to be the greatest common divisor of both of these two numbers. You really just go one by one, just pick like the smallest like power for like each of these numbers. So 1 is smaller than 2, 1 is smaller than 2 again, and 3 is smaller than 4. If you had, what if I had like times the 7 squared over here, but there wasn't any 7 over here? Implicitly, there's like a 7 to the 0 over there. And so the smaller of the two powers would be like 7 to the 0. But really, you would just say like, oh, there's not going to be like any 7s that appear in both of these numbers, so you could just ignore the 7s here. Okay, that'll be relevant when we get to least common multiple, but for now, you just kind of ignore it. Okay, so the prime factorization method is really like quick and useful if you can easily find the prime factorization, but sometimes you can't. So here's an example where the other method really shines. Let's say I want to do the GCD of 2,564 and 2,566. Okay, are you going to want to sit down and figure out what the prime factorizations for both of these numbers are? I would assume that you would not, and I also don't want to. I do not have that time. What you want to do instead is just notice, oh, if I can, if I can just subtract one number, subtract the smaller number from the bigger number, I'm not gonna change my GCD, but I'm gonna make my numbers smaller. Okay, so 2,564. Let's subtract that from the other one. They're only 2 apart, so 2,566 minus 2,564 is just 2. Okay, so what's the GCD of 2,564 and 2? Well, 2 goes into both of these numbers. They're both even, so 2 has to be the greatest common divisor of both of these numbers. So the lesson here is that both of these methods are useful in their own specific situations, and again, as with most things in math, being able to have flexible thinking is going to allow you to do things a lot quicker and be able to more effectively solve a wider variety of problems.